I'm Jack Reddy. This is Physics 2212 Lab 5. Introduction. Purpose. Collect data of a magnet falling through the conductive tube of aluminum foil. Watch the speed model on the computer. Compare the computational predictions to the observed data. Results: 1.45 seconds real time, 1.97 seconds predicted time. Predictions and assumptions. We use Faraday's law, Newton's second law, Biot-Savart law, the magnetic force equation, and magnetic flux equation. Assumptions. The bar magnet is a magnetic dipole. Air resistance is negligible. The only forces are gravity and the magnetic force. Models. The system are the aluminum foil magnet. Surroundings are everything else. Initial conditions are no magnetic force. Magnet starts at zero velocity. Procedure. Determine the end pole of the magnet. Drop the magnet. Record the time. Repeat. Average time 1.45 seconds. Notice that we notice that it falls slower in free space because of magnetic force. Here is my code. Here is the code results. You can see in my graph that in the beginning, magnetic and gravitational forces are unbalanced. In the middle, balanced forces are acting on the magnet. And at the end, magnetic and gravitational forces are once again unbalanced. Answering questions. The red or the blue current are flowing in opposite directions. Which color corresponds to the counterclockwise current and which one to the counterclockwise current? As via Lenz's law states, when viewed from above, red is counterclockwise and blue is clockwise. Discussion. Experimental versus computational. The experimental time was 1.45 seconds. The computational time was 1.97 seconds. It was a 30% difference. The computational system might have been more accurate because it had more rings, it had more trials, and it recalculated the magnetic dipole moment for a more accurate value. Potential sources of error were the incorrect magnetic dipole moment. The magnet may not have been dropped straight. It could have hit the walls of the tube. And there could have been resistances like air resistance. There also might have been human error when using the stopwatch. What if? What if the resistivity of the conductor were reduced as close as possible to zero? Why would the dynamics of the falling magnet change? Larger induced current leads to larger magnetic fields, which leads to greater opposing magnetic force, resulting in the magnet falling slower. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would decrease the current, leading to decreased magnetic force, making the magnet fall faster through the tube. Conclusion. There are discrepancies between the experimental and computational models, but either way, the magnet falls slower through the tube than it does in free space. This is because of Faraday's law. This lab is a real-world model of this law.